So let's continue from where we stopped in the previous lecture. So we looked at a special case when the angle between electric field and the displacement vector was 90 degree. We found out that dV, or change in potential, is equal to 0. Right? If theta is equal to 90 degree, then dV is equal to 0, or V is a constant. V is a constant. Okay. So which means that, let's look at this example. Okay, let's take a plane here. Okay, let's take a plane, and electric field lines are passing through it, which means that there is an electric field in that region, Okay. So what happens here is, you have to apply the logic that we learned in this case. Okay, a step further. So here it said that, here from there we understood that if you travel in a perpendicular direction to the electric field, then you will have a region or a line or a plane with equal potential points. You will have a line or a region with the equal potential points. For example, if this is the direction of electric field, and consider this as a plane, okay, and in my palm, if you take any point in my palm, you will see that the vector, the direction, this is actually perpendicular to the electric field, right? This is actually perpendicular to the electric field. Therefore, the angle between electric field and that vector, displacement vector, is 90 degree. Therefore, in this entire plane, in every point of this plane, change in potential is 0, which means this plane has constant potential. It has constant potential. Such surfaces are called equipotential surface. Okay, so for a line we can actually define a plane here. With equipotential points. So will there be only one plane, or will there be many planes? Will there be just one plane or many planes? See, here I can imagine one, right? Here I can imagine one such plane. Now I'm taking another point somewhere halfway across at the midpoint of this pen. So there also I can imagine another plane. Perpendicular plane. So I can imagine any number of perpendicular plane in this line with equal potential. Okay. So it's not just one plane or one line or one point. You can imagine any number of equipotential surfaces. Okay. For example, here you can see these are electric field lines. So I have drawn a perpendicular surface here, and in that surface potential is going to be constant. In this surface, V is constant. So one thing we have understood, the surface and the electric field direction are going to be perpendicular. Okay, so we can say that equipotential surfaces is always perpendicular to electric field lines. Is that right? Because direction of electric field is nothing but the direction of electric field lines. Therefore, we can say equipotential surfaces are always perpendicular to the electric field lines. Equipotential surfaces are always perpendicular to the electric field lines. So that is very important, and we will need it in many problems. Okay, very useful concept. Equipotential surfaces are always perpendicular to electric field lines. Similarly, in the previous class, we studied in the direction of electric field, potential always decreases. So the opposite also, it is your duty to remember the opposite. In the opposite direction, okay, in the opposite direction of electric field, potential will increase. Okay, the opposite also should be true. In the direction, it will decrease. In the opposite direction, it will increase. So that is the idea of equipotential surface. So let us see what is the equipotential surface for a point charge. So imagine a point charge. Electric field lines are going radially outwards in every direction. In all the directions, electric fields are going in all the direction. Okay. So can you imagine an equipotential surface? So what are going to be the properties? V is equal to K Q by R. For this to be constant, K is already a constant, Q is a constant, so R should be a constant. So it is going to be the collection of points around the point charge where distance is same, which means radius is same. So in three-dimensional, if you imagine, it is going to be a spherical surface. It is going to be a spherical surface. So equipotential surface for a point charge is going to be a sphere or a spherical surface. Now, will there be just one such surface or will there be many? Well, you can define one such surface for r is equal to 1 meter, and you can define another for r is equal to 0.5 meter. You can define another one for r is equal to 10 centimeter. So there are infinite number of equipotential surfaces. Okay, and two such examples are given here, r1 and r2, for r1 and r2. Now please think and find out whether potential at r2 I am writing it as v2, potential at r1 I am writing it as v1. v2, v1. Which one is higher, v2 or v1? Please think carefully and answer it in your notebook. And when I say check them, if you have got it right, very good. If you have not, do not worry, just learn it now. Okay, this is your time and time and space to make mistakes, because you can't do it during the exam. So make all the mistakes right now. v1 or v2, which one is higher? If you just go back, in the direction of electric field, potential always decreases. So I need to know which is the direction of electric field. This is a positive charge. So radially outward is the direction of electric field. Therefore, v2 is far compared to v1. Therefore, v1 is in the direction of electric field, potential decreases. So v2 less than v1. In the direction of electric field, potential decreases. v2 less than v1. Okay. So for a point charge, spherical surfaces are going to be the equipotential surfaces, and v2 will be less than v1. Okay. But for any point on this A, B, C, VA will be equal to VB will be equal to VC. Similarly, D, E and F, any point on the other equipotential surface, you can say VD will be equal to VE will be equal to VF. Okay, so that is the idea or the logic behind equipotential surface for a point charge. For a point charge. Now for an infinite line of charge, for an infinite line of charge, what is going to be the potential equipotential surface? So imagine an infinite line of charge. So for an infinite line of charge, electric field, you remember the electric field equation, 2k lambda by r. Okay, 2k lambda by r. So here also use the same logic here. Use this logic that you applied here, and if you think surfaces that are going to be equidistant from this line, surfaces that are going to points that are going to be equidistant from this line of charge will be cylindrical. It will be cylindrical, and right, it will be cylindrical. And here also you can say, here also this property, equipotential surface is always perpendicular to the electric field lines. That is valid here also. Electric field lines is actually perpendicular to the surface. It is perpendicular to the surface here. Okay. Here also equipotential surfaces are going to be cylinders. It is going to be cylindrical in shape. Okay. So here V1, V2, and similarly we can say V2 less than V1. And any point on this sphere, cylinder, any point on the inner cylinder potential are going to be equal, and any point on the outside cylinder, potential will be equal. They are equipotential surfaces. Okay, cylindrical equipotential surfaces. So VA is equal to VB is equal to V1, VC equal to VD is equal to V2. Clear? Okay, so that is the difference for point charge and line of charge. How we can define the equipotential surface. Here also field lines. Here also it is going to be hitting perpendicular to the surface. It is going to be perpendicular to the equipotential surface. Okay, so here is a question for us to do. Please read it properly. It may be a little confusing, but take your time, understand the question, and try to start doing it. I'll give you a hint. some equipotential surfaces are shown in the figure. Determine the electric field at points A, B, C. Okay, I'll tell you what are the points are, which points that we are calculating. Okay, let's calculate it here. Let us calculate it that point. Which is perpendicular. So these are equipotential surfaces. These are equipotential surfaces. So we need to find electric field, and there are potential is given in some points. So it is clear that we need to use the relation between electric field and potential here. We need to use the relation between electric field and potential here. Okay. So you can listen and let's see what are the steps involved here. So first we learned that along electric field potential decreases. So this is the direction that potential is decreasing, right? It is from 50 to 10 towards the left. Potential is decreasing. Also, electric field line is going to be perpendicular to a second point. Electric field line is going to be perpendicular to equipotential surfaces. Electric field line is going to be perpendicular to equipotential surfaces. So we know that electric field is in the direction from 50 to 10, and to get the exact direction we use the second concept. So we can draw the direction of electric field like this, a perpendicular line to all the surfaces. Okay, so that is the direction of electric field here. That is also important, to find the direction of electric field from given equipotential surfaces. What is the logic used? Electric field lines, or the actual direction of electric field, is perpendicular to the surface. It is always perpendicular. Also, along the electric field, okay, you can do perpendicular lines in two directions, either in this and either in or in that, either in this or in that direction. Okay, you can draw in this direction also. How did we decide the correct one? How did we decide the correct one? By using the first point. In the direction of electric field, potential should decrease. Okay. Now we need to find out the electric field, right? So for that we already know dV is equal to minus E dot dr, or E is equal to minus dV by dr, nothing but minus dV by dr. Okay, E is equal to minus dV by dr. Clear? Or we can write V final minus V initial, because here it is given initial and final points are given, the values are given at different points. Therefore V final minus V initial, we can write V final minus V initial is equal to minus E dot delta x cos theta, or delta r cos theta, minus E dot dr cos theta minus E dot dr cos theta. And the angle, this angle is 60 degree here, sorry, 30 degree is given. Okay, this is 30, this is 60 degree, that is 60 degree. And the distances are also given. The distance between these 2 points are 5 centimeters. Distance between those 2 points are 5 centimeters. Okay. So V final minus V initial. Just take 2 examples, any 2 lines. So I'm taking 30 and 20 here. Okay, I'm taking this line, these 2 equipotential surfaces. So Vf minus V initial, Vf minus V initial is going to be what is going to be the V. Okay, so I'm going from 20 to 30. Okay, V final is 30. So 30 volt minus 20 volt is going to be 10 volt. That is equal to minus E into distance between them. Distance between those 2 points is equal to 5 centimeters, right? Distance is going to be 5 centimeters into cos theta. So cos theta is that is the angle between what? Angle between what? Electric field. This is the direction of electric field. Angle between the direction of electric field and the direction of this distance, that is 60 degree. Therefore it will come as cos 60 here. So 10 is equal to minus E into 5 by 100 into 1 by 2. 5 by 100 into 1 divided by 2. Okay, therefore E is equal to, how much is E going to be? Okay. E is going to be, okay, so the V final minus V initial. See, this is the direction that we have taken, right? So as you can see, we have taken to the left. We have taken the direction of displacement to the left. Also, direction of electric field is clearly marked there. Okay, direction of electric field is clearly marked. So this is actually the initial point and this is the final point. We are calculating between those two. So this should have been 20 minus 30. 20 volt minus 30 volt. Okay. So this is minus 10. And there are two minuses there. You can cancel them. And electric field will be equal to 2 into 100 into 10 divided by 5. That is 400 volt per meter. Electric field is going to be 400 volt per meter. Clear? Okay, so let us revise it. Let's go to through the steps again. So you are given equipotential surfaces. Okay, with potential is given and distance between them is also given. So first is along electric field V is going to decrease and electric field lines are perpendicular to the equipotential surface. So there were two possibilities of the direction of electric field. One shown in the figure and the other is like this. But we know the first point. Electric field direction is going to be in the direction of decreasing potential. So from that we removed the second possibility, okay, and we got the direction. Then we use the relation between electric field and potential from the previous classes. dV is equal to minus E dot dr. dV is nothing but change in potential or potential difference, that is V final minus V initial is equal to minus delta R into cos theta. So here the change in position or displacement is equal to 5 centimeters and angle between field and displacement is 60 degree here. Okay, those are what we applied and we got the answer as 400 volt per meter. Direction is already marked here, so that is not a problem. 400 volt per meter. Clear? So that is the electric field. Okay. Find out the location of a point where net potential is 0 in the following cases. Find out the location of a point where the net potential is 0 in the following cases. So we had done similar questions for forces, right, or field, electric field. Apply the same logic here. Question is not at all difficult. First you need to think. If I pick a point here, if I pick a point somewhere in between, will the potential be 0? Will the potential be 0? Due to the plus 9 microcoulomb, I will have a positive value here. Due to the plus 25 microcoulomb, I will have another positive value here. And if I add them, I am not going to get 0. What about a point on the left side? What about a point on the right side? Will there be any zeros? You see, this is not a vector, this is a scalar, so there is no direction. It doesn't matter if you are choosing it on the left, on the right, or anywhere. There is no direction. Only the value matters with the sign, with the charge, sign of the charge. So here both have positive charges, which means it is always going to add together. There is no possibility of cancelling each other. Hence, in this case, find out the location. There is no location. There is no location is the answer. So, what changes should we make to the question so that we get a location of 0 potential? What change can we make to this location so that we get a point of 0 potential? Well, it's very simple. You just have to change the sign of one of the charges. Change the sign of one of the charges. Change the sign of one of the charges. Okay, please do it. Let's change the sign and let us draw the picture again. Change the sign. Now it is minus. Change plus 9 microcoulomb to minus 9 microcoulomb and find the location now. Okay, now you can find the location. Will there be 1 point or more than 1 point? Will there be 1 or more points? In the middle, it is going to be 1 point is going to be there, because positive and negative are going to add up and give us 0. Also in the left side, there may be a point. Okay, so write the equation and find out. Write the equation and find out. So like always, what do we do in such situations? We take an arbitrary point, and the distance from -9 to that point is, say, x. Therefore, the remaining distance will be 40 minus x. Now what should we do? Equate both these. Okay, or we can say the total potential is 0. Okay, so k into -9 microcoulomb. I told you to use the sign. I told you to use the sign while calculating potential. Divided by kq by r, divided by x, plus k into 25 microcoulomb divided by 40 minus x equal to 0. Cancel k, micro is cancelled. Okay, so 40 minus x by x is equal to 40 minus x by x is equal to, or there is a minus here, and if you take that minus term to the right side, that will become positive. So we can write 25 by 40 minus x is equal to, k is already cancelled, 9 divided by x. Therefore, 40 minus x by x is equal to 25 by 9. 40 minus x by x is equal to 25 by 9. Okay. Now you can simply solve it. 40 by x minus 1 is equal to 25 by 9, or 40 by x is equal to 25 by 9 plus 1. 25 plus 9 is 34. And x is equal to 9 into 40 by 34. X is equal to 9 into 30 divided by 9 into 30 divided by 9 into 40 divided by 34. 9 into 40 divided by 34. 360 by 34. So you'll get a value 360 by 34. So it should be around 10.5, right? 360 by 34 should be around 10.5, because 340 divides 34 by 10, and you get more than half of 34 again. Approximately 10.5. Clear? Now I told you there may be a point on the left side also. There may be a point on the left side also. So what should you do to find out that point? What can you do to find out that point? For that, just take the point on the other side. -9 microcoulomb is here. 25 plus 25 microcoulomb is there. Here you have your point on the left side. Take this distance as x. Therefore, this distance will be 40 plus x. Now do the same steps here, and you will be able to find that answer. Use the same steps. Okay. And you can do one more thing. That is, take a point on the right side, closer to 25 now. Okay, then do that again. So that is a homework for you. Just complete this question by finding out what happens on the left side and what happens on the right side. Okay, you have to do that as a homework. Okay. So that is about equipotential surfaces. Now here there is another question. Find the potential at the center of an equilateral triangle. Find the potential at the center of an equilateral triangle. Before doing this question, I am going to give you one value that you should never forget. You should never have to calculate it during solving a problem. Okay, all of you. Some of you may already know it. That is very good. If you do not know, then the distance from the center of an equilateral triangle to the corner is, if side is A, then this is A by root 3. Okay, if side is A, distance from the center of a triangle to the corner is A by root 3. Do not waste your precious time for calculating this. Okay, this distance is A by root 3. A divided by root 3. Never forget that. You should never have to waste your time doing that. So let's come to the question, find the potential. So how do you find the potential? How did you find the electric field at the center of an equilateral triangle? You added them according to the laws of vector addition, because field was a vector. Here, this is a scalar, so you can just algebraically add it. Okay, provided you have properly substituted the sign of the charge. Clear? So potential at center will be equal to VA plus VB plus VC, if you name them ABC. Okay, VA plus VB plus VC. What is VA? All are same charges, all are at same distance from the center, and therefore the potential is going to be the same. The value is going to be the same. There is no direction to worry about. So KQ by R, that is KQ divided by what is R? Distance from center to the corner, A by root 3. So root 3 KQ by A. Therefore total at the center will be 3 times 3 root 3 KQ by A. 3 root 3 KQ by A is the potential at the center of a triangle, equilateral triangle, at the center of an equilateral triangle. Similarly, you can calculate for a square. Okay, we don't have to do it in class. You can calculate for a square, you can calculate for a hexagon. In some of the comparatively easier entrance examination, they ask these questions directly. What is the potential at the center of a regular hexagon or a square, okay, or a pentagon? So those you can calculate as a homework. And the idea is very simple. Okay, in fact, the square question is already here. You can try it. All you need is the distance from the corner to the center of the square. So you know the side is A, then root 2A is the diagonal. So this distance is the half of that. That is root 2A by 2 or A by root 2. This is A by root 2. You should never have to waste your precious 5 or 3 or 4 seconds for doing that. It is A by root 2 for a square, A by root 3 for a equilateral triangle. So answer will be, you can directly write from here, right? 4 times KQ divided by A by root 2, or 4 root 2 KQ by A is the total potential at the center of a square, at the center of a square. Okay, now I have changed a little bit. Find the potential at the center of a square again. Okay, I'll give you 20 seconds. Think about sign of the charges have changed. So just think what will happen. Okay, 20 seconds is over. I hope you got the answer. So in the previous question, we multiplied the value of 1 with 4. So here what happens is, you got the answer, right? Answer is 0. So VA is equal to VB, and that will be equal to minus KQ by A by root 2. Similarly, VD is equal to VC, and that will be equal to plus KQ by A by root 2. So there are 2 minus KQ by A by root 2 and 2 plus KQ by A by root 2. You add them, you get V is equal to V center is equal to 0. V center is equal to 0. I am sure all of you got the answer right. I am sure about that. Find the potential difference. Find the potential difference VA minus VB in the following cases. Okay, so there are a few more questions. There are a few more questions here. Okay, so you can, these are homeworks for you. About this question, you have a line charge here, a line of charge with linear charge density lambda, and you are asked to find out VA minus VB. You can take this distance as R, okay, no problem about that. Or you can take this distance R1 and this is R2. Clear? And you have to find out VA minus VB. What is VA minus VB? That is your task. So the idea required is, see, this line charge, infinite line charge will produce electric field. Will produce electric field at A and B as well. It will produce electric field at A and B. So if you have electric field, how will you find potential difference? If you have electric field, how will you find the potential difference? That is the question here. So try it out. Try it out. That is a homework. Again, another question. Find VAB if E is equal to, in vector form, it is given in vector form. Find VAB. Find VAB. Electric field is given in vector form. Okay. So you should do something like this, right? Integral V is equal to integral RA to RB minus E dot dr, and expand it. Integral x1 to x2 ex dx plus integral y1 to y2 ey dy plus integral z1 to z2 ex dx. Okay, So that is how we calculated, and apply the limits properly. Everything is given here. All you need to do is follow the same methods that we already did in the previous questions. You will be able to answer this. Okay, clear? So these two are for you to solve it out. Okay, do it properly. And in the next class, we will be looking at a new topic called electric dipole. Okay, so see you in next class.